or you can say A into B. So now you can see that in the rate limiting step, C is there. What C consists of A and B, right? A plus B. So C consists of A and B, and that's why it should be ordered with respect to 1. A with respect to A, it will be 1, B will be 1. And I will prove this, but keep this thing in mind. Suppose if I take A plus B, uh, going to C plus D, and then C will be like C going to P, and this is RDS. In that case, your R should be constant into A into B divided by D. So divided by this. This is RDS, you remember that. So what will the composition of this C? This should be, if you look at C, C is basically A plus B minus D, right? So D will come in the denominator. So that's what it mean by this. So if the rate law is R is equal to this, the total composition of reactants in the rate limiting step is this one. A rate law to be properly interpreted according to rule 1 must be written in terms of predominant species in the reaction medium. So it should be written in terms of predominant species, then only that is true. So next, that I will explain later, this third point, but just keep that thing in mind. The terms of positive terms in the rate law is the number of independent parallel pathway. So negative terms represent the reverse reaction. So please, number of positive terms, if the rate law is like this. So R is equal to something K1 into A plus K1 into B, something like that. Then it must go by independent parallel pathway. Okay. The negative term represents the reverse reaction. So if there is a minus term here, then there will be a reverse reaction. Summation of, I will explain this again by simple examples. So but keep this thing in mind. A summation of n terms in denominator implies a succession of n steps. So if R is suppose some constant multiplied by concentration term, and there is three different terms, okay, three different terms, then in that case, uh, so what does that mean? That rate has n terms in the denominator. It means this reaction should follow at least n step, in which first step is reversible and there are two more steps. Okay, at least three steps. It can be like more than three steps. Uh, why it can be more stable? Because some of the terms may be negligible because of its rate constant. But if rate constants are not negligible, then it must consist of three steps. Okay. Then a species whose concentration appears in the single term denominator are produced in the step prior to rate limiting, rate controlling step. So if there is single term denominator, if suppose there is only one denominator, then this must have formed in the, so suppose this is reaction A plus B and giving you C plus D, and then C has gone to product C or C plus product, where C is an intermediate, and so this must have been formed in the one step prior to this. I will explain one more example. So, but just keep this thing in mind. Species whose concentration appear in the single term denominator are produced in the step prior to rate limiting step. Adding up steps in mechanism must yield the net chemical reaction. Rapid reactions may follow the rate controlling steps. Okay, alternative mechanism leading to same pattern of activated complexes are not kinetically distinguishable. So please keep this thing in mind that kinetics helps you. The rules which I am going to tell you are going to help you in limiting yourself to few of the mechanism. It may not give you a unique mechanism. In that case, you need to do more experiments. The order increases with increasing concentration when the reaction proceeds by parallel pathway but decreases when a series of steps occurs. So that I am going to again explain you in the next slide. Okay, so these are few rules which basically helps you in determining the mechanism from the rate law. So idea is that first you measure rate law in lab, and I already told you how to get the rate law. Once you have rate law, then you try to find out the mechanism. Now question is how to get the mechanism. So these rules will help you. I am first going to tell you how these rules comes, and then I am going to show you the application of that. And you will be really amazed to find out that from the rate law, it is possible to get the mechanism. Okay. Any question here? No questions? Okay, so let's go and discuss. Uh, okay, so same thing that only thing is this thing that if rate law is this, the rate composition of single step will be this, that I am going to discuss first. Except there is one exception that when water is involved in the rate determining step, then the composition can be this plus n water. This is because when you take water, then it doesn't come into the rate composition because amount of water is really very large, and so the change in this will be almost negligible. Same thing here, that R is equal to K this divided by this, which I already discussed. In that case, you can add NS2. So, okay. Now let's go and do one by one. What I told you that suppose this is a reaction A plus B going to C, and C is going to P, and this is the slow step. And so what was the first law? That the reactants which the first law which we discussed, the reactant should have composition uh, so rate law. So suppose you get the rate law, then rate law should have, if suppose these are atoms, so rate law, the rate law should give the composition of C. Rate law should give the composition of C. And suppose you have this reaction, now you write dC by dt is equal to K1 into A into B minus K minus 1 C and minus K2C. Am I right? That's how you can write the rate law for the intermediate. And you can apply steady state approximation. So this is equal to 0. C is an intermediate. So C is K1A into B, K minus 1 plus K2. And since this is a rate determining step, so dP by dt is K2 into C. So K1, K2, A into B. So this is the rate law which you will get. And now you can see in the rate law, what are the concentration term? With there should be one A and one B. So what should be the composition of the reactant in the rate determining step? It must consist of, one atom of A, if suppose these are the atoms A and B, then one atom of A or one atom of B. Okay, one atom of A and one atom. From this, you can see that C is formed from A and B. So C must have, according to law of conservation, C must have one A and one B. All right. So,
So,
yeah.
so, so second step is slow. Then how can we apply steady state approximation?
This pre-equilibrium concept I discussed in the last lecture.
Okay, okay.
Do you remember
I
pre-equilibrium concept?
no sir, I didn't watch yesterday's class, so I guess.
Okay. Yeah. So what I explained in that class is that if first step is reversible and the second step is slow, these are very fast. In that case, concentration of C will be small. And if the concentration of C will be small, we can apply a steady state approximation. So a steady state approximation doesn't say that, it is like if rate first is slow and the second step is, first step is fast, second step is slow, then you cannot always apply a steady state approximation. You can apply. Only thing you need to make sure that your concentration of C with respect to A is particularly very small. Is this okay?
Yes, sir. Yes, sir.
Okay. So only thing you have to make sure that concentration of C is small. Then only you can apply a steady state approximation. So dc by dt, I applied a steady state and I calculated the rate. And now you see this is the rate of reaction. And here you see that there is one A and there is one B. And that is basically the composition of C. Okay, because C is formed from A and B. So that's what I mean by. So if you see rate law, so you know that if there is an intermediate, there is only one intermediate, then we must have one, the composition of that intermediate must have one A and one B. Okay, so I just went in the reverse way and I proved that rate of reaction will have one A and one B. Okay, so this is very important point because that helps you in letting you know the composition of intermediate in a reaction. Okay, so I will go next and again do same thing. So what I did is A plus B giving you C plus D. And now I am telling that C is going to give you P. In that case, what will happen? Okay, what will the composition of C? Composition of C will be A plus B minus D. Am I right? A plus B minus D should be the composition. And A plus B, these are the positive terms, so they will come in the numerator and D will come in the denominator. Okay, so that's what you can see here, that dC by dt is equal to, again I apply a steady state approximation and this is RDS, rate determining step. Then dC by dt is equal to K1 A into B minus K minus 1 C into D, and this is your K2. So minus K2 into C should be equal to 0. From that I can get the value of C. C will be K1 A into B divided by K minus 1 D plus K2. And so dP by dt, rate of reaction is K2 into C, K2 into C. And so this will be K1 K2 A into B by K minus 1 D plus K2. Okay, so I know the composition of C. What will be the composition of intermediate? There is one A power 1. So this is A plus B minus D. This is the composition of the reactants in the rate determining state. The third rule, what does it tell? If there is a term in the denominator, concentration term, only one concentration term, it must have formed in a step prior to rate determining step, a step prior to rate determining step. Okay, so D, if there is a D here, there is no other concentration term. D must have formed in one step prior to rate determining a step. So rate determining a step is this. So D must have formed it here. Now I can go back and look at again this, the law which we have written. If the rate law is R is equal to this, the composition of reactant in the rate limiting step is alpha A plus beta B. If there is power 1 here, alpha is 1, beta is 1, then composition will be A plus B. That's what we got. Am I right? If the rate law is K A alpha B beta into L lambda divided by M mu and nu. Now what will be the composition of the reactants? Alpha A plus beta B plus dot 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 minus mu M minus nu N plus, if there is no water, then you can just neglect it. Okay. And now see, in our case, which we proved it, alpha was 1, beta was 1, and mu is 1. Am I right? In that case, what we got is this thing. So there are three things we are able to prove. One is the composition, and the second thing is this thing, which is also very important, that if there is only one term, particularly the product term, which is not in as a reactant in first step at least, in that case, this product must have formed in the one step prior to RDS step. So this D is not a reactant. This is a D is a product. It is also not intermediate. So D is a product. It is not involved in here. So D is a product, and so it must have formed one step prior to the rate determining step. Is this clear? Any question here?
So how do we determine the predominant species? Like there are
I
two
am
products in
assuming
this
that
in the
if
study.
it is rate determining step, then okay. So which one will be the rate determining step? The one which is the slowest step. Am I right?
Yes,
So
sir.
slowest step. So in any reaction, there will be one rate determining step. Am I right? Most of the reaction there is one. I will not say all the reaction, but most of the reaction there is one rate determining step, which is the slowest step. And rate of reaction depends on that slowest step. So getting that slow step is very important. So what will be the composition of that step? That's what we are discussing it. So that is one of the composition. But then I'm also talking about what will be, what is the product formed in, one step prior to rate determining step. So again, one step prior, you will be able to figure it out that one step prior, what is, apart from intermediate, what is getting formed. Is this okay?
Yes, sir.
Okay. So now I will go and discuss one more. So let us see A plus B giving you C plus D. And now this C again reacts with A to give you product. Okay. Now what should be composition of the reactant in the RDS? It will be C plus A. And we know that C is A plus B minus D. Am I right? A plus B minus D plus A. So there will be 2A, 1B in the numerator, and there will be 1D in the denominator. This is the composition. Now let's find out what will be the rate law. dC by dt is K1 A into B minus K minus 1 C into D minus K2 C into A is equal to 0. So C is equal to K1 AB divided by K minus 1D and plus K2 A. Again, you see, if you look at this, And now you can write d by dt is equal to K2 K1, right? A square, because this will be K2 into C into A. All right, dV by dt is K2 into C into A. C is this, multiply by A, you will get A square B K minus 1D plus K2A. Now, what happened? This is your A square B by K minus 1D plus K2A. What is, so now from, if you have a rate law, now you know what is the composition of C should be. Composition of C should be 2A plus B minus D minus A. And whole composition should be, what should be the whole composition? So composition should be your A square into B. This should be the whole composition. A plus B minus D plus A. And that's what you get from here. Right. The second thing, D is the product. D is not a reactant. Right. So D must be formed one step prior to rate determining step. This is RDS. You remember this. This is RDS. Okay. And the second thing which will also come into picture, that A must have been involved in this reactant. If there is a reactant term, then it must have been involved in reacting with intermediate. So what is reacting with intermediate, you can also know from this. Okay, D is formed one step prior to your rate determining step, and A must be reacting with the intermediate. A must be reacting with the intermediate in the rate determining step. Okay.
Sir.
Yeah.
But if A is reacting, then A should be in the numerator, no? Why below?
No, it is, you see, again, I am not talking about A is reacting with B. You see, what we are going to get composition. I just told you what is the composition. What is the composition?
2A plus B
2C.
minus D. No.
Yeah. 2, this is composition of C should be what? Here I told you what should be the composition of C. C should be,
A plus B minus D.
A plus B minus D. Am I right? And what should be the total thing? Is A plus B minus D plus A. Total. The composition. Okay. And generally what you do, that from this rate law, you can simply, what happens if suppose when this will be the slow step? When K2 is small? Am I right? Is this okay?
Yes, sir.
Do you understand this?
Mm-hmm.
K2 is small, then only it can be slow step. This I proved by, what I did is K2A, I didn't take that K2 is very small. If K2 is small, what will happen to this?
Okay,
K2
so it will
term
be neglected.
neglected. So what is left?
Okay, sir. A square B by D.
This. Am I right? And if this is there and this is slow step, means you will not get this term. So what will the composition of total reactant? There should be 2A, 1B and 1D, minus 1D. And that's what you are getting the composition. Only when this is rate determining a step, then I get the composition. Right? And that when K2 is very small, this is neglected. What rate law you will get is this one. And if you get this, then you can get the what is the composition of this. What is the composition of the rate determining step? So this thing you can again use if suppose this is not the slow step. Okay. And then in that case, I get this whole term. Am I right? This whole term I will get. Now, by assuming some of the terms at the rate determining, I can get what is the composition here. Although it is a not slow step, but if I assume that this is a slow step, then I will get the composition of this whole thing. If suppose there is a third step where B is also involved, then there will be a B term. Okay, and then even again by neglecting, you can get what will the composition of this rate determining step. Although they may not be. If it is not rate determining step, then you will get this term, whole this term. Okay. Now let's go next. If suppose I have written A plus B going to C plus P. C is reacting with R2 to give P2 and C is reacting with R3 to give P3. Okay. Now what rate law should be? So rate law should be, if you try to look at here, minus dA by dt is AB into minus, okay, K1 AB. Here in the denominator, what you will get? You will get P, you will get R2, reactant R2 and reactant R3. So there is another way to tell this. If you get something like that, it means your intermediate is reacting with P. So what is your intermediate in this? C is the intermediate. C is the intermediate, right? This is reacting with P, this will react with R2, and this is react with R3. This is another way of telling same thing, that it is reacting with all these three species. And since this one is product, so it must have been formed. Am I right? One step prior to this. These two are reactant, this must be reacting with the intermediate. This must be reacting with the intermediate. And you can see that dC by dt is K1 AB minus K minus 1 into Cp minus K2 C R2 minus K3 C R3 is equal to 0. Okay, from C you can calculate whatever you get, and then minus dA by dt is this thing, and then from that you can calculate what is minus dA by dt. Is this okay? Okay, so now let's go back and see all the how many of them we are able to look at. So I will go back again to the rules which we discussed. Okay, so these were the rules, am I right? If the rate law is R is equal to this, the total composition of reactants in the rate limiting step. It should be a rate limiting step. Then only you have, this is the composition. If the rate law is this, then this is the composition, which we just discussed how this do two rules scheme. You can basically derive it. Okay. Now let us go to third. The number of positive terms in the rate law is number of number of independent parallel pathway. Okay, keep that thing in mind. Negative term represents reverse reaction. If you remember that in the last example which I showed you, there was one negative term. It means there is a reversible reaction. Okay. The summation of n terms in the denominator implies a succession of n steps, all but nth are reversible. So I showed you that there was 3 terms in the denominator, if you remember. Okay, one is product, the second is R1, and this is R2. So it means there should be at least 3 steps, in which first one is reversible. Species whose concentration appear in the single term denominator, okay, are produced in a step prior to the rate controlling step. Okay, so that's what I told, that if there is one term here, it must have produced in the one step prior to the rate determining step. Okay, finally, adding up the step in mechanism must yield the net chemical reactions. So rapid reaction may follow the rate controlling step. What does that mean is that suppose you ended up with the 2-step mechanism, but if you sum them, the 2 steps, you may not get the total reaction. In that case, there may be few steps which are very fast, which you have left out. So just by looking at what is left out, you can be able to get that fast step. Okay. The order increases with increasing concentration when the reaction proceeds by parallel pathway, but decreases with a series of steps occurs. Okay, so let me again go back. Okay, same thing, I wrote minus dA by dt. So for the same reaction, you will be able to get this equation. Okay. And if you get this equation, what you got, there is, 2 positive. Okay, so 2 positive terms, it means that there should be parallel pathway, and you can see in this reaction there is a parallel pathway. C is reacting with R2 to give you P2, C is reacting with R3 to P3. So there is parallel pathway. So third term you will be able to explain that thing. Okay, this is what a summation of n terms in denominator implies a succession of n steps where at least one step is reversible. And if you look at here, so this is for this reaction. So there are 3 steps. So there are 3 steps in the denominator. Okay. Then if there are 3 terms in denominator, intermediate can disappear in 3 or more steps. So that's again you can see that intermediate is disappearing in this one, intermediate is disappearing, or means it is reacting in this step, intermediate is reacting in this step. So there are 3 different ways in which intermediate can disappear, and that's why it is being shown here. Okay. Okay, so now we know the some of the rules. Now let us see how can we apply this. Am I right? So let me start with one example, then you will understand probably in a much better way. Okay, so let me give one example. 2Fe2 plus. This is the whole reaction I am going to write, plus Tl3 plus, giving you 2Fe3 plus Tl plus. This is the whole reaction. And then this is the rate of reaction, dTl 3 plus by dt is equal to K Fe 2 plus whole square into TL3 plus divided by Fe2 plus into plus K dash Fe3 plus. This is the rate law. Now propose a mechanism. Can you propose it now? How many steps you can think of? Two. Okay. Two steps, because there are two terms in denominator. So at least two steps. So I'm going to write two steps. Okay. Now, tell me, can you tell anything else? Is there any terms in as a product in the denominator? In the denominator, can you see, is Fe2 plus a product? No, this is reactant. Am I right? What is this?
Fe3 plus product.
This is a product. So where it will be formed?
Reversibles.
Am I right? Prior to this, if this is a slow step, okay. Now think about what you can write. This is what? This is a reactant. तो ये कहाँ पे होगा?
Intermediate.
Okay. Is this okay?
Yes, sir.
Okay, great. Now think about that. If suppose this step is slow, it means I can neglect this term. Am I right? Because there should be k here. It is only because we are writing k dash, that's why I am not. But there will be a rate constant k, suppose k2, so there should be a k2. Only thing is that we have divided here. So just neglect it. And then tell me what is the composition of reactant. How many iron? कितना आयरन होना चाहिए? How many iron should be? You see here. How many iron here? 2 iron, am I right? Because this is square and there is 1 here. So how many left? 1 iron. How many TL? कितना TL होगा? There is nothing in the denominator. So how many TL? 1? Is this okay? देखो यहाँ पे देखो क्या है, मैंने क्या कहा था, इन सबों का ऐड करना है. So 2 Fe minus 1 Fe is 1. 1 TL minus 0 TL. So 1. Again, that can also be done with the charge. चार्ज कितना होना चाहिए? अगेन ये क्या चार्ज है? 4 प्लस 2 2 4, यहाँ पे प्लस 3 और यहाँ पे माइनस 3. आई एम नेग्लेक्टिंग दिस थिंग बिकॉज दिस इज द slow step. I am thinking that this is a slow step, so I am neglecting this. So what is left? 4. ऑलरेडी आपने एक Fe2 प्लस ले लिया है, तो एक आयरन चला गया और इसमें से 2 चला गया. So क्या बचा? TL. What should be the charge?
2 plus.
This is what? Intermediate. तो यहाँ क्या फॉर्म होगा? Now tell me what should be here. Can you tell me?
Sir, Fe2 plus plus TL3 plus.
TL3 plus. Yes, that's all. That's how you write mechanism. यहाँ पे क्या बनेगा?
TL plus plus Fe3.
Fe3 plus
TL
plus
plus
TL plus. You know the product. Add कर दो. Do you get this thing?
yes, sir.
Okay? Okay. So let's go to another example. You should try yourself. It is really fun. If you understand it, it is very easy for you to do. Okay? So let me see. This is the same example. So this is the example which I have given, and this is the same thing. Okay. Let's see. Oh, I don't have. I have to find out one example, but in this I don't have. Let me find out another example. Give me 1 minute. Okay. 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 Now just write this mechanism. CCH3Cl plus OH minus. Okay. So let me write down myself, then I can, because here answer is given, so you may. Okay, so I have question. I will write here. Okay, so this is the example. CCH3 thrice, okay, Cl plus OH minus gives you CCH3 thrice OH plus Cl minus. Okay, rate is minus D C CH3 thrice Cl by dt is equal to K C CH3 thrice Cl into OH minus divided by K dash Cl minus plus K double dash OH minus. Okay, now solve this. Okay, how many steps?
2 steps.
2 steps. Okay, 2 steps. So in this, which one is product, which one is reactant? बताओ क्या प्रोडक्ट है क्या रिएक्टेंट है? Cl minus is
Product.
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 So this should have been formed here.
Step earlier.
OH minus कहाँ जाएगा?
Reactant.
Reactant.
Because this is a reactant. So OH minus. Okay. Now let's go get the composition of this step. What I need to neglect? This term. Because this should be slow step, then only I can write this. So I just remove this. Okay. Now tell me what should be the composition. How many carbon? How many carbon? बताओ कितने कार्बन होने चाहिए? नहीं कार्बन है ना? हाउ मेनी कार्बन? 4. Good. How many hydrogen? 9. How many chlorine? 9 ही होगा या 10 होगा? 10 होगा ना? इसको भी ले लें. 9 plus 1 10. How many chlorine? बताओ क्लोरीन कितने होंगे?
1.
हाँ, एक यहाँ है, एक यहाँ है, क्या होगा?
Zero.
0.
0. Okay. चार्ज बताओ. चार्ज शुड बी.
सर सो हाइड्रोजन हमने डिनोमिनेटर वाला सब्ट्रैक्ट कर दिया.
इसको नेग्लेक्ट कर रहे हैं, याद रखना. राइट. So don't keep this thing in mind. Okay, एक Cl था चला गया. 9 ये हाइड्रोजन, एक हाइड्रोजन यहाँ. चार्ज कितना है? ये 3 टर्म देखो. चार्ज कितना है? 1 minus here, but 1 minus cancels out. 0. Okay. OH minus पहले से है. So what is left out? इसमें चार्ज क्या होना चाहिए इस साइड?
Plus.
प्लस. बचा क्या? यही बचा. CH3
whole 3.
CH3 thrice plus. So this should have been CH3 thrice plus. और यहाँ तब क्या होगा?
CCH3Cl.
CH3Cl. OH minus is not involved in the first step. First step is this, and then you get the product. Okay, you see, in this I have not done anything else. I just know the rate law, and on that basis I am able to write what should be the mechanism. But keep in mind, always I tell you, because there will be some cases in which, just by kinetics you cannot tell what is the unique mechanism. But this is going to be true if the rate law is this. Composition is not going to different. It may be one H is this side, one O is this. That is a different issue. Or for example, CCS3 OH is here, but that will be product. Means any something where the composition will be like this, then only it will be. Hello, can you call me after 5 minutes? Oh, okay. Yes. Is this okay?
Yes, sir.
Yes, sir.
Yeah. So kinetics is very important when you are trying to, when you are trying to know the mechanism. Just by looking at the rate law, you will be able to tell what is the mechanism. Most probably, yes. Certain time you have, if it is a complex, then issue is different. You may need to do some more experiment, but that's okay. But kinetics is very important. That's what I am trying to say. So in the last lecture, what I showed you, that if you have some experimental data and from means kinetic data, I'm talking about experimental kinetic data. For example, aggregation, if you are looking at kinetics of aggregation, if you can look that in your lab, then just by taking few models, different kind of models, to try to obtain a corresponding your simulated data just through by solving differential equation. If you can fit that to your experimental, then that model is true. But out of 4 models, your data will not satisfy 3 of them, only it will satisfy one of the model. And then you know that this model is the mechanism. So that is one thing which is particularly done when you are dealing with very complex reactions, where there are more than few steps which have comparable, although small but comparable rate constant. Then it is difficult for you to tell which is the rate determining step. Okay, which is the rate determining step. But today I also showed you how to get the mechanism from the rate law. And that is particularly important when you are dealing with organic or inorganic reaction. It is not that difficult to get the mechanism of reaction if you employ kinetics, or if you can look at the kinetics of that process in a lab through different means. Okay, any questions? Is it clear or not?
Yes, sir.
Yes, sir.
Okay, so
Yes.
yeah, I will discuss few more cases. It is not the end of that, but now you know at least for simple reactions how to get the mechanism. Okay, so I will stop here.